Okay. Cool. Okay, I can see Phoebe. Thanks everybody for sticking around. I'm happy to welcome Professor Phebe Vayanos from the Departments of Industrial and System Engineering and Computer Science at the University of Southern California. Phebe is also Associate Director of the Center for AI in Society. And that has been one big area of her research, looking at developing methods from robust optimization, machine learning, integer optimization in order to address problems in society. And today she's gonna tell us about one such problem which blends robust optimization and preference elicitation. So Phoebe, please go ahead.
Thank you, Elias. Thank you both for organizing this wonderful series. And I'm very grateful to have been invited to present in front of such a big audience. So thank you both. So today what I'd like to talk about is a recent paper of mine concerned with active preference elicitation. So in particular, what we're looking to do here is ultimately make recommendations to users, so about decisions that they should make. However, so we don't really know the user's preferences. And the idea is that before making a recommendation, we would like to ask a moderate number of strategically chosen questions to be able to learn the user preferences to then make a better recommendation. The outline for my talk is as follows. I'm going to start with a bit of a motivation for the problem I'm looking at. I'm then going to introduce the various elements of my model. I'm going to talk then about two elicitation strategies, offline and online elicitation. I'll present some numerical results on both synthetic data and real data from the homeless management information system. And then I'm going to discuss some extensions that my research group is currently working on. So decision support systems, also known as recommender systems or recommendation systems, have become ubiquitous in our daily lives. We're increasingly using them to help us with decision making. So for example, we use Google Maps. The hope is that they can help us solve complicated decision-making problems where the number of alternatives is just too high to consider individually, or where there's uncertainty and so on. Of course, when we're using a decision support system to help us with decision making, well, this system needs to understand our preferences to be able to recommend things that we are likely to adopt. For example, if I'm looking at Google Maps on the right, there's different ways in which I could get from this dot in Inglewood to, say, the University of Southern California. Each route has different characteristics in terms of, say, the travel time, the distance traveled, and so on. And which route I'm going to prefer depends on my personal preferences. And researchers in decision theory, in psychology, in economics, in marketing, in OR, and also more recently AI have actually been looking at this problem of basically trying to understand the preferences of the user. In my talk, I'm going to be taking this perspective of multi-attribute utility theory, which states that when choosing one alternative over the other, the user is actually basing their decisions on the attributes of the two options. So say I'm looking to buy an iPad, what I'm going to look at is the price of the iPad, the type of display it has, etc. And I'm going to weigh in the different factors in deciding my favorite option. But these are not the problems that actually motivated this research. What motivated us is the homelessness crisis in LA. Currently, there's around 60,000. These numbers have grown this year. There's almost 60,000 individuals that are homeless in the LA area, and there's only enough housing resources to help support just a few of them. So we have partnered with the Los Angeles Homeless Services Authority, which is the entity in charge of allocating housing resources in LA, with the aim to improve the way in which housing resources are currently being allocated to be able to mitigate homelessness. The current policy in place is based on the vulnerability score. The idea is that we should allocate the more supportive resources to the people that are the most vulnerable and therefore less likely to exit homelessness on their own. So when they come into the system, individuals are assessed by answering a questionnaire Depending on how they answer each question, they get a score for that question. The scores are added up together to give the vulnerability score. Based on the vulnerability score, they are triaged into 3 buckets. The most vulnerable bucket, the people there will be waitlisted for permanent supportive housing. The people in the middle are going to receive rapid rehousing, which is a less supportive voucher-based short-term intervention. And finally, the people that are the least vulnerable, they will only receive services. A drawback of this policy is that it's not tied to outcomes. And so what we would like to do in our research is to design a policy for allocating these resources that is actually tied to outcomes. But of course, then this raises the question of what outcomes should we be looking at? And so in our discussions with LAHSA, we came up with 3 desiderata that we're interested in. First of all, we would like our policy to be fair. We would like it to be efficient. We would like it to be interpretable. But of course, what each of these 3 things means is not clear. Different people would interpret fairness and efficiency differently. We would be able to tolerate different degrees of, say, unfairness if we were to increase efficiency sufficiently and so on. So the question of actually understanding what fairness means, what efficiency means, what interpretability means, and then how to prioritize each of these things is a complicated question that it seems has been a recurring question in the minds of policymakers at LAHSA. One popular technique for eliciting preferences in the marketing and economics literature is to ask pairwise comparisons in terms of the outcomes that we want to evaluate. So let's say in our current setting, what this would mean is that we could show outcomes of different policies and then ask users to tell us which one they prefer. So for example, in this figure on the left, I'm showing the outcomes of policy A, which in terms of exit from homelessness is not very fair by race. On the other hand, it has a very high chance of success for an arbitrary individual in the system. And then we have the policy on the right, policy B, where we can see it's very fair in terms of its outcomes by race, but it is less efficient than policy A. So here we're really just looking at one dimension of fairness and one dimension of efficiency, but still if I ask you to compare policy A to policy B and to tell me which one you prefer, I would get some understanding of your preferences in terms of fairness and efficiency. And so by asking a series of questions of this type that are becoming more and more complicated, but each of which is not too hard to answer, I can learn something about your preferences. Of course, the question is that there's a very large number of policies with different characteristics that I could be asking about. Also, we have more dimensions than what I have actually shown here. And so the question is, well, which questions should I be asking? Which pairwise comparisons should I be asking to gain the most useful information? So let me tell you a little bit about how we model the various elements of this problem before moving on to the actual problem formulation. So first of all, we have a model for the candidate items or policies, which can be used to either build comparisons or make recommendations. We characterize each such item, each such policy by its attributes. In the spirit of multi-attribute utility theory, we also call these attributes features. Each feature would be, in this case, a measure of interpretability, efficiency, or fairness. And then each policy is basically characterized uniquely by this J-dimensional feature vector. We then have a collection of such policies, which we call the query set, which can be used to build queries or pairwise comparisons for the user. So for example, so here we have, let's say, I policies, and to build a query, I can just choose 2 of them and ask the user, in this case, the policymaker, do you prefer, say, policy 3 or policy I, which is the same as saying them, do you prefer policy I or policy 3? And this enables us to build this comparison set, from which we are going to draw to ask the user comparisons. Ultimately, what we want to do is to make a recommendation. This recommendation should come from what we call the recommendation set. This set could be, for example, the same as the query set. Basically, I may be just looking to recommend one of these policies. It can generally be a discrete set, or it could be a polyhedral set intersected with some integrality constraints and so on. The point is that my ultimate goal is to select one item from this recommendation set to provide to the user, and this item should be in some sense as good as possible. To model user preferences, for the time being, I'm going to assume that the user is rational. Of course, we relax this assumption in the paper, but this helps me streamline my exposition here. In this case, we can represent user preferences using some unknown utility function u, which is going to map the characteristics of any given policy to some real number, which is going to quantify how much our user likes the item we are recommending. The user can then respond, say that they prefer policy X over policy Y if I ask them to compare these two policies, in which case this would be the same as saying that their utility for policy X is strictly greater than their utility for policy Y. They could answer, of course, that they prefer Y over X, in which case we would have the opposite inequality on the utilities. They could also reply that they are indifferent, which would mean that their utilities for the two items are equal. Again, we're making this assumption of complete rationality just for ease of exposition. I understand that saying that the utilities are exactly equal may seem very restrictive at this point. We propose to model user preferences following a line of research in preference elicitation, which proposes to not work with distributions, but rather to work with uncertainty sets, where we're going to assume that the set of utility functions that we're considering actually lives in some set. This assumption was made in a line of work by Boutillier and al. In the AI literature, by a line of work by Tubia and al. In the marketing literature, and more recently by Bertsimas and O'Hare in the OR literature. Moreover, just like in these papers, we make the assumption that the utility function of the user is actually linear. So for any given feature vector X, we can express linearly the utility that the user has for that policy in this case. The utility, the vector of utility function coefficients u is, however, unknown and just known to belong to an uncertainty set u0, which we assume to be polyhedral. This assumption is not very restrictive. For example, if I don't know anything about the vector of utility function coefficients, I could say that it lies in a -1, 1 box. So all of its elements are between -1 and 1. Because we can arbitrarily scale this utility and still make the same recommendation, this assumption is non-restrictive. What we want to do is to build pairwise comparisons. So we want to decide on a sequence of, say, k pairwise comparisons. Each pairwise comparison is nothing more than a pair of items. For the k-path comparison, I'm going to call the first item, the first policy in the comparison, iota kappa, and the second one, iota kappa prime. When I make such a comparison, so I'm asking the user, do you prefer item iota kappa or iota kappa prime? They have three options, three responses they can give me. They could say, I prefer the first item, I'm indifferent between the two items, or I prefer the second one. We encode this set of possible replies, and by the way, we don't know which reply we're going to get at the time when we ask the question. We encode them by these response scenarios. We have three response scenarios, which we encode in this value of S kappa, which can be either 1, 0, or -1. And we have this set, which is just a possible set of response scenarios, which has just these three elements. So let's think about what happens. I have here three items, item 1, item 2, and item 3, and I assume that each of them have just two features so that I can represent these items, these policies in two-dimensional space. If I ask the user to compare item 1, say, and item 3, really what they're going to tell me is something about the sign of U transpose x1 minus x3. So let's see what happens if this is my original uncertainty set as I ask questions and I get responses. So initially, my uncertainty set is the -1, 1 box. If I ask the user to compare items 1 and 2, what I'm asking really is, does your utility coefficient lie on this side or on this side of the hyperplane? Let's say they respond that they prefer item 1. I'm left with the upper half. Then I can ask another question. Let's say compare item 1 and 3. If they respond that they prefer item 3, I'm left with the bottom part of that half space. with the bottom half space. And so this set here would be my new uncertainty set after I have asked my questions and observed the answers to the users. So this new uncertainty set clearly depends both on the questions I asked, J, and the answers I received, S. We can also represent this set mathematically, right? It would just say that I augment it with constraints whose sign is going to depend on the response that I got to the various questions I asked. Note that this set involves strict inequalities, which are going to complicate a little bit our life. Once I have asked queries and observed answers to the queries, I can make a recommendation. We investigate two types of recommendations. One is the risk-averse recommendation, where we want to select from the recommendation set the policy or the item that's going to have the highest worst-case utility, where the worst case is taken over the updated uncertainty set after I have observed the answers to the questions I asked. We also investigate a regret-averse recommendation problem, where we want to recommend the item that has the lowest worst-case regret, where the regret is nothing more than the difference between the utility of the item I recommended and the utility of the item I should have recommended had I known the true utility. For this talk, I'm going to focus on the risk-averse recommendation setting, but in our paper, we have all the derivations for the regret-averse case. We investigate two elicitation problems, the offline elicitation problem and the online elicitation problem. In the offline elicitation problem, we decide here and now which policies to ask about. So in other words, which pairwise comparisons to make. We then observe the answers to the pairwise comparisons. And in the second stage, we recommend a policy that's going to meet the needs of the policymakers based on the information that we have at that point. This offline elicitation setting is suitable for paper-based surveys and when all people, or if we want all people to get the same questions. This problem is solved offline. Let us now formulate this problem mathematically. So the idea is that we can model this problem as a 2.5 stage robust optimization problem. In the second stage, we solve nothing more than the recommendation problem. However, before solving the recommendation problem, we have one decision stage where we can select which questions to ask. Having chosen which questions to ask, we observe the answers to those questions, and then we make the recommendation. In this problem, this set, Si, is just a set of response scenarios that are compatible with some utility vector. In other words, we're saying the user must be rational. They cannot just be responding randomly stuff, right? Their responses need to be compatible with some underlying utility function. This problem, we claim it integrates the questions to ask with a downstream recommendation. Indeed, depending on the structure of this recommendation set, I'm going to be changing the questions that I ask. This is in sharp contrast with existing approaches from the literature, which just base the choice of questions on some information criterion. And therefore, independently of the downstream recommendation, they would always ask the same questions. Let us study a little bit the complexity of this problem. So some observations. This set Si, S of iota is decision dependent, but also remember it has this quite complicated condition that says that for the iota chosen, this set must be non-empty. So it's kind of complicated to model. This set is not only decision dependent, but it also involves these strict inequalities that model the preferences of one item over the other. We have the following theorem on the complexity of this problem. First of all, if the recommendation set is convex, so if the set from which I can draw items to recommend is convex, the problem is actually polynomially solvable, and there is no benefit in asking any questions, so I get no value by asking questions at all. On the other hand, evaluating the objective function of this problem is in general NP hard, even if the recommendation set consists of only 2 items. Motivated by this second complexity result, we show that we can actually formulate this offline optimization problem as a mixed binary linear problem. At the high level, the idea is that we can eliminate the dependence of S on iota, and we can relax the strict inequalities to be loose and drop the indifference reply. In other words, it would never help the user to reply that he is indifferent between the two options. This is, actually, let me highlight a little bit the steps then of that derivation. Having eliminated the dependence of this set on iota and having made these inequalities loose, we can interchange this max and the mean, provided the set R has finite cardinality, and we can then index X by S. We then obtain a max-min optimization problem, which can be reformulated as an MBLP using standard robust optimization techniques. This is the mixed binary linear problem. One challenge, though, is that this problem involves an exponential number of both decision variables and constraints. However, you observe that for any fixed tau and iota, it has a very nice decomposable structure. And what we propose to do is to solve it using a tailored column and constraint generation approach. We start with a relaxed version of our problem, involving only a subset of the scenarios, and so a subset of the decision variables and constraints. Solving this problem, we obtain a iota, which is a choice of queries to ask. We then feed that choice of iota into a feasibility subproblem, which, among others, optimizes over the scenarios. This feasibility subproblem will either return a certificate that iota is actually optimal in the true problem we wanted to solve in the master problem, or it will return a violated scenario S to add to the relaxed master problem. This procedure is repeated until convergence. In the online elicitation setting, we ask one question at a time, and we are allowed to adapt our choice of question to asks to the questions and answers we have observed in the past. This is suitable for computer-based surveys, or if we are happy to ask different questions from each individual. This problem needs to be solved online, so we need to have access to a computer when we solve it. We propose to solve this by means of a conservative approximation. Intuitively, this problem, you can write it down, is a multi-stage dynamic optimization problem with decision-dependent uncertainty sets with exponential number of response scenarios at each stage, so it's very, very intractable. However, this conservative approximation, which still integrates the elicitation and recommendation phases, can be solved very efficiently using enumeration. Basically, for each choice of question, we can evaluate its worst case performance, and then we choose the best question to ask. So this is very fast. We will see in our results that actually it performs very well relative to the state of the art. So let's have a look at numerical results. First of all, on synthetic data. Here, what we did is we generated various data sets that have different numbers of policies and different numbers of features. On the first row, we increase the number of policies. Second row, we increase the number of features. And third row, we increase the degree of mistrust that we have in the answers of the user. On the x-axis, we have the number of questions. On the y-axis, we have the worst case utility of the item we end up recommending. Our approach is the red approach. The blue approach is random elicitation. There does not exist another approach in the literature for addressing this problem. We drew, for random elicitation, we drew 100 questions, so 100 sets of questions of cardinality k. This is the range in the shaded area. The blue line is the median. What we can see is that our approach always outperforms random elicitation. Note that 100 is only a small number of possible queries we can ask relative to all the possible queries that there exist. For example, here, I could ask 60 times 59 possible questions. In terms of speed, although evaluating the performance of random, which is shown here in blue, is quite a bit faster than obtaining the best question to ask. Because we need to perform many evaluations of random, you need to multiply this number by the total possible questions I could ask. And so ultimately, it's a lot faster to just immediately compute a query. We also note that no one knew how to evaluate the performance of random before our approach. We also look at the online setting. So here I want to emphasize that 0 would be, so here again, it's the same layout. I'm just using online elicitation to generate queries. Red is still our approach and blue is still random. But in the online setting, there exists other approaches in the literature for computing questions to ask. These are based on this analytic center approach. They basically say, they're heuristics that say that at each stage, I'm going to select the query that passes the closest to the current analytic center, the analytic center of my current uncertainty set. The idea being that if it passes close to the analytic center, then it slices the uncertainty set in two in some sense and gives me a lot of information. What we can see is that these green approaches are actually performed similarly to random, so there's no real benefit. On the other hand, our approach converges very often to 1. 1 is the utility I would get if I actually asked all the questions. So here we can see that by asking just say 5 questions, we can get maximum utility, although there are 60 times 59 possible questions I could actually ask. We show that although we do not really optimize rank, so this figure is about ranks, our approach, again, the red approach, recommends items that are ranked a lot higher than all the other approaches. This figure looks even better when we actually optimize regret. I'm not showing these results here. We then consider, we then evaluate the performance of our approach on real data. We simulate, I don't have much time to go on the details, but we simulate using real data 50 policies for matching homeless individuals to housing resources. Basically, we generate random samples in a bipartite graph that match different types of individuals which are put into these queues to different types of resources represented by these servers. For each policy that we sample, which just represents a way of connecting servers to queues, we record 21 features. We include in these 50 policies the first come first served policy and the current policy. We then evaluate the performance of our approach on this new data set of 50 policies with 21 features. In this case, we looked at optimizing worst case regret. So here being low is better, having a regret that is close to 0 is better. 0 represents the case of no regret, so what I would get if I asked all the questions, and 1 represents my starting point. It's what I would get if I didn't ask any questions. What we see is that our approach has far lower regret than random. Again, this is the median performance of random, and this is the range. These are runtimes. I will skip this for the time being. We also show the results of our online algorithm. What we can see here is 1, again, what I would do if I recommended immediately an item without asking questions, and 0 if I ask all the questions. We see that our approach converges to 0, so that by asking just 10 questions, we can recommend an item that has very low regret almost always. In fact, the rank of the item we recommend is always 1. This is the worst case rank by just asking 7 questions. So just by being strategic, no matter what the preferences of the user are, in the online setting, we were able to always recommend the first item, their preferred item. We are working on some extensions of this work to the multi-stakeholder setting. Indeed, many decisions need to be made collectively. For example, in the current pandemic, several hospitals have put together committees that must deliberate on how to triage and prioritize patients for scarce healthcare resources. So we believe that extending these ideas to the multi-stakeholder setting can be valuable to help policymakers and decision makers in these systems reach consensus faster. We have very encouraging preliminary results that I'd be happy to talk about later. To give you an idea, the various stakeholders that are involved in this case are doctors, patients, the government, and the population at large. I am very grateful for funding support for this work from Schmidt Futures, USC, the Metrans Transportation Center, and United Way LA. We recently got a grant with United Way to help pilot some of these results in the real world. My talk is based on this first reference that I have at the top, which is available on Optimization Online. The other papers on this slide are the other approaches that use uncertainty sets to elicit and then recommend items. Thank you all very much for your time.
Great. Thanks a lot, Phoebe, for a nice talk. Again, I think for this one, we're just gonna stay and take questions in the individual breakout rooms that Alex is gonna set up in a second. And so with that, if you need to leave, please feel free. Otherwise, if you'd like to just chat or have questions for either of today's speakers, please just stick around and you'll be assigned to one of the respective rooms.
Right, and also you can ask questions on the Discord anytime you want afterwards, and there's specific channels available for both of these talks. Yeah, thank you very much, and I'm going to stop the recording now.